title because of the limited time, and the focus today will be on helium. So I thank the organizers for inviting me. And I actually never met Fano during my association. However, I've had a long association with well, Ravi and Chris would periodically give me reports of what Fano thought of my experiments. And so I have a rather unique opportunity here to get back. So here's my Fano story, and it actually has a NIST connection. Somewhere in the late 80s, I was visiting NIST, and Tom Lucatorto, who I just met for the first time, agreed to show me around some of the laboratories. And we're walking down the hall, and Tom goes to me. He says, why are you interested in seeing the labs? Aren't you a theorist? I said, no, I'm an experimentalist. And he says, but why are you always hanging around those Fano guys? So, of course, growing up in the Robbie Ramsey school, that was kind of like a knife through the heart, right? So after years of therapy, I recovered. I'm a better person for it. And here I will tell you about really how Fano School did influence some of my thinking, particularly in strong field and thinking about multi-electron sorts of effects. And what I'll do here is I'll cover some of the fundamentals of as we go along, as we need in this strong field regime. And again, I like to keep my focus for most of this talk on understanding double ionization in helium. Now, let me just acknowledge the people here who have done the work. Jan Chalupka, a postdoc who, as of next week, will join the faculty at William & Mary. Robert Lafong, a former Stony Brook student who now works at Sandia. And Joanna Rodetti, a graduate student from Stony Brook, who's carrying on some of the experiments. And my longtime collaborations with Pierre Agostini of Saclay and Ken Kuhlander of Livermore. And in fact, let me say now that many of the calculations you will see are a product of Ken's work. Okay, I'd like to start with this single photon picture to make a point about what's necessary to learn something from these experiments. And of course, in '63, there was this important paper by Madding and Codling where they studied the photoabsorption around the n=2 threshold of helium. And what they saw of these series of autoionizing levels, this famous series of autoionizing levels, and of course, the Fano profiles were seen in it, but that wasn't the point of the paper. The point of the paper was the assignment of these autoionizing levels, and that was followed by a companion paper famous companion paper by Cooper, Fano, and Prats, which show that these states here really must be described and indicate a breakdown of this single electron or independent electron picture. Now, it wasn't possible at that time when these experiments were done at MBS to study the two-electron in the two-electron continuum. The synchrotron was only capable, I guess, of producing radiation in this area. But then within 4 years, Carlson actually observed the two-electron ionization single photon. It was actually quite an amazing experiment. He used conventional X-ray tubes. They were rather broad-banded, and he excited helium anywhere from 1/4 to 1/2 of a keV photons, and then recorded this photoelectron spectrum. The blue area indicates all the single electron ionization. The red area, these few counts he sees here, are the signature of the double ionization occurring in helium. And here's where the problem lied. The problem lied in the fact that the double electron events, as Peter was pointing out early, were just a small fraction of the total ionization occurring in helium.
I think the difference was that the Madden Codling using photographic detection, just looking at the total absorption cross-section. which doesn't show big changes.
Okay. I also...
The synchrotron reached well.
Oh, it did reach that. Okay. Okay. So to break this problem of seeing these kind of rare events required new tools. And in the early 70s, there started to become more and more available synchrotrons. They started to become user facilities. They were tunable, but they offered this advantage of high average power and high repetition rate to study rare events. And people went about that in the single photon community studying ionization and started to make incredible progress, making very detailed measurements. Here I show the total double ionization cross-section as a function of photon energy, only to make the point with this insert here, which is the photoelectron spectrum, that we know that this simple curve, the dynamics vary from a Wannier sort of behavior, strong final state correlation to some sudden approximation limits. And these experiments that I show here show that quite dramatically. Here are all the single electron satellite peaks that you would expect in the ionization of helium. And here's the continuum electrons that Peter was pointing out, showing this evolution from a flat distribution Wannier behavior to something that looked more like a shake-off phenomena. And even more detailed information started to follow because of this renaissance in this tool. Here's an experiment of Alan Vetz where he shows the detailed angular correlation between the two electrons. And this, again, provides very detailed information that could be compared to experiments. So what's different now in the strong field regime compared to the single photon? Well, again, our focus is helium here, so I'll talk in terms of how we can conduct the experiments in helium. And for one, the experiments work in a non-perturbative regime. That is to say that the laser field is comparable to the Coulomb field binding the electron. And in the case of helium, in our studies, it's about 0.2 atomic units of field amplitude imposed by this external field. The other major difference, as Peter was showing, is there's our photon. In fact, here's a blow-up. Our photon is just a little red photon of 1.6 EVs. And what we're going to try and do is doubly ionize helium, which is bound. The two electrons are bound by 79 volts. So the process is extremely nonlinear, if you want to think about it as photons. Now, historically, as these intense lasers started to become available in the 70s, right away there were many results showing that if you expose some atom to an intense field, you can strip off more than one electron. And here's an example here of krypton being exposed to 1 micron light, and they could see everything the krypton-4. Okay? This paper that I quote here is actually the first paper to recognize that there was something more occurring that could indicate a multiple electron excitation. And that's shown here in this red region. So you're looking at the total rate ion yield as a function of intensity. And the krypton 2 plus curve seems to have this break in slope. That is, it could not be described by just a single rate. And in this paper, they suggested that this was evidence of direct ionization. And direct ionization to the group at Saclay meant direct 2 electron ionization at that time. It wasn't until 10 years later that the similar evidence was seen in helium. And this is an experiment by Fittinghoff at Livermore. And here, again, you see the total rate for the production of helium and helium-2 plus as a function of intensity. And in this shaded region is the region of non-sequential ionization. The solid curves are, as Peter described, calculations of the sequential ionization. That is, the just sequential stripping off of 1 electron at a time. And this was done using an ADK model, which is a cycled average tunneling model, which I like to now think about ionization as tunneling instead of photons, since these fields are so intense. So Okay, this is quite simple for everyone. Here, I mean, an atom placed inside a field plates will have an effective Stark potential, and if the field is strong enough, the atom has some rate of exponentially tunneling the continuum. And of course, if I just change the polarity of my field plates, then my rate is the same. It's just I'm kicking the electron in the other direction. Now, what I have is an optical field of low frequency, where you can think of this Stark potential as wagging back and forth each optical cycle. And on every half cycle, there's some probability of tunneling. So you have a picture like here, where red is my optical cycle, blue is the tunneling rate. So I'm kicking out electrons in little bursts located around the extremer of the field. Now, once it gets into the continuum, I know what the electron does. It just wiggles in the field, and that wiggle energy is quite significant. The displacement of that electron is on the order of 50 to 100 atomic units. So for most of the time it's in the continuum, the electron is just dominated by this strong, its motion is dominated by this strong electric field. Now, if you do classical analysis of that, well, what would you find? If this is the core, my electron gets kicked into the field. Well, one trajectory may wiggle it, and it leaves the vicinity of the core. But if you look at certain classical trajectories, the electron will kick out but drift back and revisit the core. And this is the essence of this recollision model or rescattering model in strong field physics. This is the place of the essential physics of what we observe in strong field phenomena. So it's like the two-step process, as Peter alluded to. The major difference here is that the electron is dragged off by the optical field, propagates for half of an optical cycle before it collides with the field, collides with the core. Now, at that point, it could give rise to elastic or inelastic scattering off the core, and those things could be observed in the experiment. And we spent a lot of time trying to understand the single electron ionization in terms of this model. So here's helium, again, being exposed to a field of about a petawatt per centimeter squared. Here's the electron distribution. Notice again, this is red light, 1.6 eV photons. We're seeing electrons going out to 500 EVs. It has this kind of characteristic shape of decreasing rapidly, followed by a change in slope, followed by another cutoff. Now, the blue line is a calculation including this interaction, the subsequent half-cycle interaction with the core. And you can see it describes this data quite well. Now, this is sensitive to what the potential looks like. If we don't include any rescattering, we get this red line. Okay? So that's just accounting for the simple drift motion given to this electron as it leaves the core. If we only included Coulomb scattering, we'll underestimate the amount of rescattering you see in the helium experiment. It was actually Ken using more accurate model potentials for helium that got this overall rate correct. So we spent a lot of time studying the single electron dynamics because there was still the question as of 1990 is in terms of all the strong field phenomena we see, what was the underlying physics that connected it all together? And that came to fruition with this rescattering model. We finally had a model that seemed to indicate how strong field physics occurred, and these rather, I think, accurate tests show that that model was indeed correct. Now, again, we came back to the issue of needing new tools to get new insights. And now you're again looking at the total rate as a function of intensity for ionization of helium this was a rather beautiful experiment done by my former student, Barry Walker. And the first thing to notice that these rates are recorded in the experiment over 12 orders of magnitude. What made that possible, the tool that we needed, was also a higher duty cycle laser. And in the late 80s, in my laboratory, in Gerard Moreau's laboratory, we had demonstrated that using a certain type of amplification, you can actually generate very intense pulses of light at a repetition rate of 1 kilohertz. Nothing compared to the synchrotron, which runs at 100 megahertz, but certainly it was a big jump in technology from the usual 10 hertz systems that we were using. To tackle the helium problem, though, we also needed very short pulses, and that came about with the titanium sapphire laser, and that made this experiment possible. So here again now is this sequential ionization calculated by Ken using this single active electron approximation. And the red curve, you can see, fits the data over this full dynamic range. The green curve, which is the ground state of the ion, ionizing, single electron ionization, is shown here. And again, you see this rate here that's not described by this sequential ionization. So that was the area of interest, again, of whether this was direct two-electron ionization, or as we were calling it then, non-sequential, which was a bit more nebulous. Now, you see, we have the same problem that they had in the early 60s in terms of learning more about this process. Here's a plot of the double ionization scaled against the single ionization. And here's this non-sequential region. And you can see the rate is on the order of a part in 500. So we're looking for a rare event in a sea of single ionization. So it's the kind of needle in the haystack. And these kilohertz lasers really made it possible for us to start applying more sophisticated coincidence techniques to try and identify those two red electrons. So a series of experiments started to occur in about 2000. The first two I list here were people from the synchrotron community bringing their knowledge and techniques, particularly this technique of cold trims, which just measures the translational recoil of the ion. And they applied it to things like argon and helium and neon. Later on, electron-ion coincidence, true coincidence techniques were applied by all these groups. The Crete group by Demetrius Haralabides on xenon, the Michigan group led by Phil Buxbaum on argon. But our emphasis, again, was in this understanding the helium ionization, double ionization. So this is to give you an idea of how this spectrometer works. I mean, the laser will fire, create these ions. The electrons will go up through the detector field free. Then we apply an acceleration voltage and push the ions towards the other detector. And in this manner, what we can do is look at the electrons and tag them against the ions as long as we create less than one ion and no more than 2 electrons per shot. So it's a very demanding experiment in terms of duty cycle. So here are some results of our helium coincidence runs. This is done at an intensity of about a petawatt per centimeter squared. The blue curve here is the single ionization that we were looking at earlier, again showing this characteristic shape of a rapid decrease in the electron yield, followed by this plateau region, which is described by the rescattering picture. And the red shows the counts of helium double ionization. Now, just to get a feel for the difficulty of this experiment, even though the count rate was 2 in 500 for detecting double ionization, this data was collected for 205 million laser shots, We accumulated 45 million helium hits during that time, and the number of coincidence events was about 1,000. So this was over 40 hours of, say, data collection. But you see there is a large difference in what the distribution looks like in comparison to the single ionization. In fact, the double ionization distribution is much more hotter or energetic than the single ionization spectrum. And you can do that experiment again at half the intensity, and again you see this characteristic shape. Although the electron energies are now lower, characteristic fall off followed by this plateau. The double ionization just looks like a monotonic decrease extended to some high energy. Just note here at this particular intensity that we detect electrons, and here's where we kind of run out of sensitivity at about 200 volts energy. So let's turn back to this rescattering picture. And it was Paul Corkum who recognized that besides the inelastic process, there's also the possibility of having an E2E type process in this rescattering picture to release 2 electrons. So let me show you in terms of the current data that it's indeed consistent with this classical or this quasi-classical interpretation. So what I'll do here is I'll just release some electrons at particular phases of the field, let that electron propagate. When it comes back to rescatter off the core, and those are the only trajectories that I'll look at, then I'll just say, does it have enough energy to free the second electron, or at least excite the second electron in helium to the first excited state of 40 volts? Because at that point, as long as it's in the first excited state, the field will ionize the rest. And then I'll only allow for the electron to either backscatter or forward scatter in this field, and I'll just let the incoming electron give up enough energy to free the second electron. That is, that second electron only has 0 energy initially, and all the excess energy is taken up by the first electron. And then just calculate what type of energies I would expect to get from that. So here I'm showing this is the initial phase that is in the optical field. So this is from the extreme of the field to the node of the field. And the blue is the backscattered component of the electron at this intensity. And you can see I expect to see electrons out to about 200 volts in this simple model. The forward scattering are much less, and of course the second electron in this very simple picture would have no more than, say, 75 volts of energy. But indeed, that's kind of the essence of what we see. And if that's not clear, let me show you something Ken Kuhlander did. This is just a 1D calculation of helium, 2-electron model. And Ken made various assumptions in the differential cross-section here. It's not a quantitative comparison, but you can see here that the electrons, the backscattered electrons, extend out here in 4 of these units, which is somewhere around 200 volts, and the forward components are much less. So indeed, I think what we're seeing in helium with red light is this E2E process. Now, everything is not exactly consistent with this rescattering. Clearly, if I can do my helium experiment at 800 nanometers and take it down to very low intensity, at some point there will be a classical threshold at which this rescattering mechanism should shut off. However, I won't be able to do any coincidence experiments at such a low rate. I mean, that's just impossible at this point. So here you see in data for helium at 400 nanometers. So I just doubled the frequency of the light I was using. And now, again, you're looking at the ratio of double ionization to single ionization as a function of intensity. You see this increase. This gray line indicates where the process stops. That is, I deplete the ground state of this helium atom. And now, the point here is this blue region indicates at 400 nanometers the classically forbidden region of this E2E process. And what's surprising here is that the rate that you see around saturation is identical for 800 and 400 nanometer light. But clearly, the physics must be different. And that's the point that we're at right now, is understanding these differences and trying to see how these two-electron dynamics do evolve in this field. We're now in the process of doing a coincidence measurement at this 400 nanometers, trying to get some idea what the electron distributions are like. We're also hopeful that someone like Ken Taylor, and we have been discussing it, will be able to calculate at this frequency something that could be directly compared to the experiment. How am I doing on time? Okay, so let me just then continue and get off on the helium for the moment and show you evidence of, that we believe, of a different type of ionization or two-electron ionization mechanism that's occurring in this strong field. So now I want to change your thinking a bit about the ionization and go back to this photon picture that's been used by the two previous speakers. So what you see here is this is xenon. Here's the continuum for the xenon atom. And it takes a certain number of photons for me to ionize this atom. Now, what I'm plotting here is I have a pulse in time that's Gaussian, and that is signified by the shape of, or the shift in the continuum, okay? The amount of quiver energy that occurs even in the case of studying xenon at this lower intensity is on the order of 3 to 4 photons shift in the continuum. So in a strong field, we knew this since the 80s, in a strong field, the electron is actually bound more deeply in the field, right? How much work do I have to do to free the electron in the field is the amount of work I have to supply to break it from the Coulomb, and then the extra amount of work I have to do is to start it quivering in the field. Okay? So there's a real shift in that continuum, and as Tony was showing, there will actually be channel closing where a certain number of photons at a lower intensity, which would have freed my electron, no longer does that in the strong field. And I can see things like ATI peaks, and here's now xenon, and here's the xenon electron spectrum, and you see these nice periodic peaks that are separated by a photon energy. That is the ATI structure. This line here indicates where classically I would have expected to see this rapid drop followed by this plateau. And you can see xenon doesn't behave simply as my semi-classical physics would say, but we also know that the interaction energy that's occurring in this type of system is very different than helium. And now let's look in this green region, and there's even more surprises, again showing that the details of the atomic potential matter. And if you look more closely, the green spacing again is 1 photon separation, that is the ATI peaks. And now you see this finest structure. The finest structure is the Rydberg structure. This was observed by the Bell Labs group led by Rick Friedman back in the late 80s. And it's easy to understand that Rydberg states in the atom will also shift like a free electron. That is just in terms of this quiver energy. And at some point in time and space, it will shift into resonance, and I'll get an enhanced rate in my photoelectron spectrum. So essentially, what we're doing in this experiment is instead of changing our frequency to do spectroscopy, we're tuning the atom to meet our photon energies and to see its structure. So this was a rather beautiful experiment. So now let's apply our coincidence technique to this atom. And now this is now in momentum units and atomic units. Here's the xenon. You see this nice ATI structure. And now we do the coincidence experiment. And you can see the double ionization spectrum is not much different than what it is in the single ionization. It has clear ATI structure. In this case, the average kinetic energy is slightly hotter than it is in the single ionization. And upon closer inspection, again, we're now back to energy. Here's again our API structure. Here's the black is the single ionization. The red is the double ionization. The double ionization seems to show the same Rydberg structure that we see in the single ionization. Well, after sending the students back into the laboratory, they convinced me that this wasn't just an artifact of how they were doing the experiment. Then one was really surprised that double ionization would go through the most least likely states that you would expect to contribute to such a process. That is Rydberg states, pretty good independent electron states, which may be an indication that the signature that we see in xenon for non-sequential ionization is not direct ionization, but some higher order sequential process that we're in the process of understanding. So there's yet a lot to learn about double ionization in this strong field, and I hope I convince you that we're making some progress. So thank you for your attention.